Now we are going to see what is a phase rule. So we know phase rule is an important tool that is used for quantitative treatment of systems in equilibrium. Quantitative treatments means accurate measurement of systems. It enables us to predict the conditions that must be specified for a system to exhibit in equilibrium. We know heterogeneous system is a system consisting of two or more different phases that are present in equilibrium. Such systems can be studied by phase rule. This phase rule is given by Willard Gibbs in 1876 on the basis of thermodynamic principles. So, this rule predicts qualitatively the effect of pressure, temperature, and concentration on heterogeneous equilibrium. So, the definition for phase rule is in a heterogeneous system in equilibrium that is not affected by gravity, electrical, and magnetic forces, the number of degree of freedom of the system is related to number of component and the number of phases existing at equilibrium. It is mathematically given by f equal to c minus p plus 2. This f denotes the number of degrees of freedom, c the number of components, p the number of phases, and 2 will be the additional variables of temperature and pressure. We have to know what is a phase. So phase is a homogeneous, physically distinct and mechanically separable part of a system which is separated from the other parts of the system by definite boundaries. That means a phase must have a definite boundary. For example, if you take a gaseous mixture, it consists of only one single phase. So, they are completely miscible. Air is a mixture of so many gases we all know. That is oxygen, hydrogen, nitrogen, carbon dioxide, water vapor. Everything will constitute for air, but they are completely miscible and it forms a single phase. So if we are taking two or more liquid phases which are completely miscible with one another, they form a single phase because they do not have a definite boundary to separate. So example for such systems are alcohol, water, chloroform, benzene and so many things. They constitute the single phase. Suppose if we take two liquids that are immiscible with one another, they form three separate phases, two liquid phase and one vapor phase. Example for that one is benzene and water. Okay. Then component. Now we are going to see what is a component. It is defined as the minimum number of independent variable constituents which are required to express the composition of each phase in a system. So if we are considering water system, it consists of three phases. The chemical composition of all the three phases is H2O but are in different physical form. Hence the number of component here is 1. So each independent chemical equilibrium involving the constituents count as one equation. The condition that a solution be electrically neutral also counts as one equation if ions are considered as constituents. So for example, if you take sulfur system also. So sulfur will be existing as monoclinic sulfur, rhombic sulfur, liquid sulfur and vapor sulfur. So for this system, the component is 1 but the phases are 4. Now we are coming for degree of freedom. So it is defined as the minimum number of independent variable constituents such as temperature, pressure and concentration which should be specified in order to define the system completely. So for this we are taking the water equilibrium as an example. Water exists in three phases we know and the component is 1. Hence this system does not have any degree of freedom. when all three phases are in equilibrium. So the system is non-variant here. A gaseous mixture containing nitrogen and oxygen, which is completely defined when three variables are given. So here the system is said to be trivariant, that is F equal to 3. Then phase rule. So the greater the number of components in a system, greater is the degree of freedom for a given number of phases. So the number of phases is maximum. The number of degrees of freedom is 0 for a given number of components. For one component system, P is 3. Two component system, P will be 4. Three component system, P will be 5. Advantages of phase rule. It provides a simple method of classifying equilibrium states of system. So we can classify the equilibrium easily. And also the phase rule confirms that different systems having the same number of degree of freedom behave in the same manner. Then it is applicable only to macroscopic systems and not concerned with the molecular structure. It predicts the behavior of systems with changes in variables that govern the system in equilibrium. For example, we can predict how the system works when we change the temperature by keeping the pressure constant, or keeping the pressure temperature constant, and how with the temperature change how the system behaves. These and all can be predicted with the phase rule. It also predicts that under a given conditions whether the number of substances taken together would remain in equilibrium or it involves in some interconversion or elimination. So it does not give the information about the nature of the reactants or products in the reaction. It finds extensive use in the study of many heterogeneous systems. It is extremely useful in the extraction of metals. Limitations. The phase rule is applicable to heterogeneous system in equilibrium. So it cannot be applied for non-equilibrium systems or the systems which are very slow to attain the equilibrium state. It can be applicable only to single equilibrium state. It never give information about other possible equilibriums in the system. Variables such as temperature, pressure and composition are only taken into account in Gibbs phase rule, but the electric and magnetic influences have not taken into account. And also all phases in the system must be present under the same temperature, pressure and gravitational force. And also solid or liquid phases are not finely divided. If it happens, the deviation will occur. Phase diagram. So phase diagram is a diagram in which 1 degree of freedom is plotted against another degree of freedom. The number of phases that exist in equilibrium depends upon the condition of temperature and pressure, or temperature and composition, pressure being constant. These conditions are determined experimentally and the values of the variables can be exposed graphically by appropriate coordinates. These diagrams are called phase diagram. It is very easy to describe the phase behavior of a system by such diagrams to investigate the conditions in which various phases will constitute the system. So it consists of two diagrams. One is pressure temperature diagram and another one is temperature composition. Application of this Gibbs phase rule to one component system. So for one component system, the phase rule can be given by F equal to C minus P plus 2. So here the phase diagram is obtained by fixing the variables such as temperature and pressure. So we can take water system as an example. So water is an one component system Water exists in three possible phases: solid, liquid, and vapor. These can exist in four possible equilibrium, that is solid liquid, liquid vapor, solid vapor, and solid liquid and vapor. So these can be given by the phase diagram is represented like this. So we can explain the phase diagram using the phase rule. So the curve OA is called the vaporization curve. It represents the equilibrium between water and vapor. At any point on the curve, the equilibrium will be existing is water and water vapor. The degree of freedom of the system is 1, that is, the system is univariant here. This can be given by Gibbs phase rule. So this equilibrium will extend up to the critical pressure, that is 374 degrees Celsius. Beyond the critical temperature, the equilibrium will disappear and only water vapor will exist. Now we go for curve OB. The curve OB is called sublimation curve of ice. It represents the equilibrium between ice and vapor. At any point on the curve, the following equilibrium will exist, that is ice and vapor. The degree of freedom of the system is 1. The system is univariant here. This is also predicted by phase rule. This equilibrium will extend up to absolute zero, that is minus 273 degrees Celsius, where no vapor can be present and only ice will exist. Curve OC. The curve OC is called melting point curve of ice. It represents the equilibrium between ice and water. At any point on the curve, ice and water will be present in equilibrium. The curve OC is slightly inclined towards pressure axis. This shows that melting point of ice decreases with increase of pressure. The degree of freedom of the system is 1 here. Point O is called the triple point. The three curves OA, OB and OC meet at the point O, where three phases like solid, liquid and vapor are simultaneously at equilibrium. This point is called triple point, and at this point ice, vapor and water three will be in equilibrium. The degree of freedom of the system is 0 here, that is, the system is non-variant. The corresponding temperature and pressure at the point O are 0.0075 degrees Celsius and 4.58 millimeter. The curve OA dash is called the vapor pressure curve of supercooled water or metastable equilibrium, where the supercooled water and vapor will be in equilibrium. Why this equilibrium is happening means sometimes when water is cooled below 0 degrees Celsius without formation of ice, this water is called supercooled water. Supercooled water is unstable and it can be converted into solid by seeding or by slight disturbance. Then we go for the areas AOC, BOC and AOB, which represents water, ice and vapor respectively. So in order to define the system at any point in the areas, it is essential to specify both temperature and pressure. The degree of freedom at this areas is 2, that means it is bivariant here. It is bivariant here. So with all these factors, we can completely define one component water system with a single phase diagram. So this is the important application of phase rule. Thank you.